So hello everyone, my name is Umar Jamil. I work at Mistral AI. Today I'm going to talk about how we trained our model Magistral, so how we added reasoning to a model. This is a really important topic because most people want their model to be thinking, and that's what reasoning is about. So before we deep dive into that, I would like to put a little bit emphasis on the fact that we have a diverse audience here. So I will try to keep the talk high level on some technical details, but feel free to just interrupt me and ask me to go deeper at any moment. So let's talk about how we arrived to reasoning models. Like what was the journey that we had to do to arrive to introduce reasoning. So initially we had the large language models that were trained on a lot of data taken from the web to predict the next token. So language models are, first of all, machine learning models that just learn from data. And the way they learn from data is that they take some text and they try to predict what is the most likely next token based on the data they have seen during training. Then people started realizing, hey, these models cannot just generate text. You can actually conversate with them if you just build your training data in a particular way. So we started building training data that looks like conversations. And then because the language model is just trying to complete the text, it will just complete the conversation. So we started going from this, which is a prompt, to generate a text. For example, Mistral AI is an AI lab, and the model will just generate whatever text it believes is reasonable for this prompt. We started going to this form of text, where we could have like a system prompt, where we can give instructions to the model, the user query, so questions that the user asks, and the model will try to generate a text, which is an answer, based on the data it has seen. So the model is not changing anything in this architecture. We don't change anything in the way we train the model. We just change the data format so that the model is not just completing any text, it's completing a conversation. And we keep generating text until we reach, for example, the end of text token for this particular turn in the conversation. And then we can add another question from the user, and the model will try to complete the next part of the text. This is how we build a multi-turn conversation. We train the model to handle a variety of text, a variety of tasks. So we can ask the model to complete, do question answering. We can ask the model to generate articles. We can ask the model to summarize articles, etc. So the variety in the training data is really important for the model to be able to perform its task. However, if you ask the model, given this training, to do a very complex task, the model will not be able to do it out of the box. And this is pretty understandable, because if I ask you a very complex question, the only answer that you will be able to give me in 1 nanosecond is the only thing that comes on top of your mind, right? So you don't have enough time to think about it. So what we really want to give is the model the ability to have some time to think about it before answering, or a scratch pad to take some notes and then come up with a better answer. This is really important for very complex tasks, for example, math problems, for example, code execution, for example, agentic task where the model has to choose about what is the next function to call or what is the next action to take based on the conversation so far. Again, the model is not doing anything different. It's still predicting the next token, but we want to give it the ability to predict the next tokens that help it produce an answer that is more accurate for the downstream task. And the goal of this talk is to teach you a little bit of how we give a scratch pad to a model. Before we do that, we need to introduce what is reinforcement learning, because that's a big ingredient here. So I don't know if you own a pet or a cat. Have you ever tried to teach your cat to shake your hands? So the way you do that is you usually start with a cat that has no knowledge of shaking your hand. So you take the cat and you try to, for example, guide it. You go close to the cat and you do like this. And of course, the cat will not shake because it has never been trained to do so. So maybe you take your other hand and you guide the paw of the cat and you try to have it shake yours. And if the cat is able to do it successfully, you give a biscuit to the cat. Now, so basically you're rewarding a behavior of the cat. And then the next time you put your hand, the cat will connect with the fact that there was a biscuit, so the cat is more likely to do it. And you can optimize this training or this reward model by saying, hey, if the cat is not only shaking my hand, but it's also, I don't know, jumping, then I give it 2 biscuits. So the next time the cat is trying to jump and shake your hands, you give it 2 biscuits, so it will keep reinforcing the idea that, hey, if I do this, I will get a biscuit. And this is how we play with language models. We give them a reward for coming up with a correct answer so that they're more likely to come up with the correct answer. But we don't teach them how to arrive to the correct answer. And this is the magic of reinforcement learning. The way we train the cat, we don't teach the cat how to do a task. Eventually, we hope that the cat can come up just by using biscuits. So we start maybe with a very simple case, and the cat, for example, can shake his hands. Eventually, the cat learns that it needs to perform some interaction with a human to get more biscuits, right? So we start playing with more complex scenarios in which we don't tell the cat how to perform its task, but we just let the cat play with it. Eventually, if we see the behavior is something that we want to reward, we just reward it. And then the cat will roll back and say, hey, what did I do? I should do more of this. And this is what we do with language models. Why can we do it with language models? Because in reinforcement learning, what you need is an agent that can perform some actions given a state. So for example, a cat that is in this position in front of human, this is the state of the cat. And the action that the cat takes is shake hands. Among all the actions that the cat can take, right? The cat can also move to the right, move to the left, or sit down, etc. But the cat chooses to use this action because it will give some reward. We can see language models as reinforcement learning agents as well, because language models, basically what they're doing, they are predicting the next token, which is choosing among all of the list of the actions, which are the next tokens, the one that most likely is the correct one. So we want to teach the language model to choose the actions, so a series of actions, so a series of tokens, such that they lead to a correct answer for a given problem. And that's how language models can be seen as reinforcement learning agents, because given a particular state, which is a prompt, the language model should be able to choose the next action, so the next token that will lead to a reward. And the RL pipeline is made in such a way that it optimizes the parameter of the language model to reinforce the series of actions that lead to a correct answer. So far, so good? Perfect. So this is the Magistral paper. This is our reasoning model. So, okay, the paper is online, so you feel free to read it. I will go through the steps that we present in the paper, so like all the details of our pipeline, etc., etc. So let's start with a little bit of reasoning, reinforcement learning algorithm that we used. So I think before we do this, let's go to another slide, and then I come back to this one. I think it's easier. So what you need to introduce reasoning to a model is you need a set of questions. Set of questions where you have the corresponding answer. So for example, for math problems, you have the problem statement and you have the final answer. You don't need the steps to perform on how to solve the problem. You just need the final answer. These are called verifiable rewards problem, like verifiable problems. For a coding problem, what you need is a problem, like write a chatbot or like a bot that can download data from Wikipedia, for example. What you need is a downstream unit test that you can run on to check if the code is correct. You don't need necessarily to have the exact code that performs the task. What we want to do is to have the language model generate for a given question or a problem statement a output, and then we can verify it against the ground truth. And if it's correct, then we reward the model for having chosen the right sequence of tokens, and then the model is more likely to do it in the future, just like the cat before. So what we need in this pipeline is generate a lot of trajectories for a given questions. So for example, for a math problem, we generate 20 variants of solutions from the same prompt. You can do that because language models are sampling for each step. With a higher temperature, you can sample a lot of responses. Some of them will be correct, some of them may not be correct, so we need to verify them. The ones that are verified are saved somewhere, and we score them, so we assign some reward with them. If the problem, for example, imagine a student during an exam, a student that solves a math problem but without showing the steps. Well, you could say, okay, it's 10% of score because probably you memorized it, right? If the student is also writing the steps, maybe you give 50% because, hey, you also show all the steps. if the student is also showing formatting all the text in a perfect way, aligned, and writing in a decent manner, then you also give a higher score, right? And this is the way we score with language models. We can choose the level of score that we want to give to each of the output, because not all outputs are the same. So if you solve the problem and you solve it in a particular format, like respecting correct grammar, using LaTeX the correct way, using the formatting that we really wanted to use, you don't mix languages, so you don't write a little bit English, a little bit Chinese, etc. We give it a higher reward. Then we take this generated output, these scores, and we feed it to an RL algorithm, the one that we saw before, and we optimize the model based on this. We say, do more of the things that give you high reward and do less of the things that give you low reward. And this is the whole point of this algorithm here. So we sample a question from a data set of questions. We sample responses, capital G number of responses for the same question. Then from the policy that from the generator, basically this means the generator. And then we try to maximize this objective. This is the GRPO objective from the DeepSeek paper. We actually do a modified version, so later I will talk about why we need to modify it. We check, this basically is called the advantage term. It tells you how better this choice of token is better compared to all the other tokens in the same position. It's higher for higher rewards, lower for lower reward. This is telling the model how the ratio of how much the model wants to choose this particular token compared to the model at the previous iteration of the training. And this is minimized compared to clip loss, because this is telling me if the model wants to do, for example, wants to choose this token with a likelihood that is 3 times more than the previous likelihood, means the model is super confident that this token is the right choice. We want to restrict this confidence. We want it to clip it between two thresholds. We don't want the model to be overconfident about its choice, because it could introduce noise in the training process. Plus, there is this term, which is basically the KL divergence of the policy that they are trying to optimize, so the model that we're trying to optimize, compared to the model before the RL training. This is basically to enforce that the model doesn't go too far, like doesn't change drastically compared to the base model. Now, this was the vanilla GRPO objective. We modified it a little bit. First of all, we got rid of the KL divergence. So this term here that was forcing the model to not change too much, we got rid of it. Because we want the model to change, actually. And actually, this is what typically happens in reinforcement learning. The model actually changes a lot. And if you look at the typical loss of reinforcement learning, they always teach you, oh, the loss should go down. Actually, it goes up. And it's fine that it goes up, because the KL divergence is just growing. Anyway, we learned that, okay, KL divergence is kind of restricting the possibilities of the model. So we got rid of it. If we want to go back to the case of the cat, basically it's like telling the cat, hey, you should behave like a cat, don't behave like a dog. But we want the model to become a dog. It's fine. We want the model to become creative. We also got rid of the fixed threshold, so the upper threshold and the lower threshold. One was restricting the model to become too confident. One was teaching the model to become less confident about the choice. We believe that we want the model to become overconfident, so we want a higher threshold for how much the model can become overconfident, but we want to keep a lower threshold for how much we want the model to become less confident. Which means that if the model thinks this is the right token for this position, just do it. And also there was a bias introduced. Okay, this is little details, but basically by normalizing on the length of its responses was introducing a bias in the learning process, such that the model preferred correct answers with a shorter length and the wrong answer with a longer length. Why? Because if you look at this term, basically for the same advantage, a lower length will give you higher contribution to the final objective. So basically you're telling the model, hey, for the correct answer, you should stay short. We don't want that. We want the model to be creative. So we can go through the details, like why we needed, okay, the KL divergence, I kind of explained it. The loss normalization, I said the vanilla implementation favors the short lengths for correct answers and the longer responses for incorrect answers. Advantage normalization is basically to reduce the noise. We can skip this part for now. Relaxing the trust region upper bound, basically it's the two thresholds that I showed before. So we want the model to be, it's okay to be overconfident about the choice. It's like our cat says, every time I'm here, I should shake my hands, even if there is no user in front of me. It's fine. But we don't want the cat to be too afraid to even raise their hand. That's the kind of the idea behind these two thresholds. And we also realized that a lot of times the model is not even able to solve, because you take one question and you generate many trajectories from it. Sometimes it happens that none of them are correct, so we just eliminate them from the group. As I said before, there is a big part played by the reward model. So just like with the cat, we play with biscuits. With models, we play with rewards. So we reward the model for choosing a correct format for the response, and that's where the thinking tokens come from. So we want the language model to output its thinking process between two tags, thinking and /thinking. So if the answer is correct, but the model doesn't respect the format, we give it a very little reward. So the model is incentivized to not only produce correct answers, but also to follow this format. This is really important because sometimes people like to watch the thinking process like collapsible, right? So we need to know where is it. That's why we need this one. And for math problems, we want the output to be inside a boxed, which is kind of a latex format. We want to be in a place where we can easily find it with the regex, like we can just parse the output and find the answer, so we can compare it with the ground truth. If we cannot find the answer, we don't know which one is the answer among all the numbers that are in the output. Of course, the answer should be correct. So for math, we want to verify it against the ground truth. So we have it in our data set of questions. So every time you do RL with the verifiable rewards, you need to have something that you can verify. And in the case of mathematics, it's the final answer. In the code, we basically run the code and we check if it passes the unit test associated with it. We also penalize the length, and it's a soft penalty and a hard penalty for very long answers. So we want to basically the model to not overcomplicate its thinking process. Why? Because a lot of times in the thinking process, basically model go along one thinking process. They say, oh, no, I made a mistake, let me go back. If you don't disincentivize this, the model will just do it all the time. So because inference costs are high for bigger models, so we want to also kind of put a budget for the number of tokens that we generate for this thinking, because a lot of times they are kind of not really useful for the model. They are just an intermediate step that the model doesn't even use. And on top of this, we were the first one to add the language consistency. So if you use a language model with a reasoning model, you will see that in the thinking process, sometimes the model will mix languages. So sometimes you start thinking like in English and then switch to Chinese and then go back to Japanese and I don't know, French. We are incentivizing the model to always stick to one language. This is something that we can show here. So we have a question in, I think, Hungarian, and this is the thinking process in Hungarian. All right, so I can talk a little bit about the infra that we use for this. So I think let's go to the picture. Basically, to run an RL pipeline, you need a lot of GPUs, of course. Not only the training part, but especially the generation part. Because the training part, the beauty of the transformer is that once you have a sequence of tokens, you just feed it to the model, and in parallel, the transformer will generate output. But the inference process is always autoregressive token by token, which means that to generate answers, it's pretty slow. Now, the infra that we built was a particular case because it's asynchronous. Like most RL pipelines, basically what they do is you have questions, you generate some answers, you verify them, score them, build a batch, feed it to the trainer, and then run gradient descent to the trainer, and this updates the process. Then you put the new weights of the model into the generators, generate new trajectories, score them, build a batch, feed it to the trainer, update the weights of the model, etc., etc. However, as you can see, every time you're training, the generators are not working. So we wanted to avoid this because it's a big infra cost, and also it's like a lot of GPU time wasted. So the way we do it is as follows. We take some questions, we start generating answers, and we keep generating. We never stop. Once we have enough of them, we feed it to the trainer pipeline because we have scored them, we know the log probabilities, etc. We train the model. Now the generators are still working. They're generating the next answers for the next set of questions. However, most other labs, they basically stop the generation because you don't have the new weights that you need to generate the new set of trajectories. What we do instead is we change the weights on the fly while they are generating token by token. So some tokens may be generated with the previous version of the model, some tokens with the recent version of the model, some of them with the, like 2 or 3 policies older. Now this, and this is exemplified here, so there is a policy change on the fly. So maybe a response was the first 100 tokens of the response were generated with the previous version of the model, and the last tokens were generated with the most recent version of the model. Honestly, it's not a big deal because a little bit of policyness, it's okay in RL. Actually, this is what we do with importance sampling. That's how we optimize RL pipelines. And we should also share a recipe on how much of policyness is okay in this kind of infrastructure in the paper. So yeah, this is the RL infra that we are using. So generator never waits for long sequences to finish. We just keep them running always at max speed. And while they are generating, we just change the weights on the fly using the latest version of the weights from the training pipeline. Now we trained the 2 variants of the model. We started from our Mistral medium. And we were the first lab, I think, to do pure RL to arrive to our reasoning model. Like, we take the Mistral medium 3, and then we took a lot of data on math problems. Do we have enough time? Do we have enough time?
Yeah, we have 4 minutes.
Oh, 4 minutes. Okay. So we took a lot of questions, math problems, code problems, etc. We ran our RL pipeline, and that's how we achieved reasoning, just by using rewards. So it's basically just training your cat. But then we realized the smaller model may not always generate good trajectories because most of them, they could not lead to any reward, right? So you could either keep waiting for some miracle to happen and the model comes up with the right answer by chance, or you give it a kickstart. And that's like taking your cat and taking the paw of the cat and say, hey, you need to do like this, and the cat will do it, right? This is the kickstart. So basically what we do is that we generate traces, SFT traces, so like generate the whole answer of the question using the trained Magistral. We feed it as we fine-tune the small model using this data. So the small model is now better, more likely to be able to generate correct answers. Then we run RL on top of it. And we also share a recipe on which one is more convenient to do. Like, should you go for RL? Should you go for SFT? The recipe is that the best way you can, first of all, we prove that you can achieve reasoning only with RL. And then we also share like which kind of data will give you what kind of improvement. Like, should you go for code data or should you go for math data, and which one is going to improve what performance? And the results are that if you do only math, actually coding abilities will also improve. And if you do only code, math abilities will also improve. And also we share like recipe on what is the right mix of RL versus SFT. And okay, these are some details on how you should choose the batch and mini batch. I think we can skip that. We also show that basically we analyze the weights of the model, and we saw that basically as the model improves in its reasoning, so improves in its reward, the model favors to have longer responses. This is the meaning of this graph. On top of this, once we finish training Magistral, we never actually teach it to handle multimodal tasks. We never teach it how to improve in its multimodal reasoning, like how to extract better answers from images or charts, etc. Actually, it happens for free. So once you train the model using just math and code, the model will be able to improve its reasoning also on images. And that's the free lunch. And this is an example. And we also show like if it's convenient to train using an existing model, like for example, you can take a Kimi, R1, etc. You take its traces, what kind of performance improvement you can have. And this is an ablation that we run also on the paper. And that's it, guys.